You are given points in a high-dimensional space. For the sake of simplicity, let us look at 2 dimensions. If you create a scatter plot of it, and you get something like this, then this could give you the feeling that your data could be clustered here in 2 different clusters. However, you don't know which point belongs to which cluster, or with which probability it belongs to which cluster. You know that the Gaussian Mixture Model, or the multivariate extension of it, allows you to assign a probability to each of the points belonging to one of the D clusters that you think that are in the data. However, in order to assign this probability, you need the parameters of the Gaussian Mixture Model. So your task is that you have some data which are n points in k dimensions. Here it's roughly 100 points in 2 dimensions, and to find the parameters of the Gaussian Mixture Model. And the parameters of the multivariate Gaussian Mixture Model are the cluster probabilities, the mu vector, and the covariance matrix. And we need this for all of the D clusters that you think that they are in the data, and here it's 2 clusters. But how can we find these parameters? And the solution is to use the expectation maximization algorithm, shorthand EM, which we're going to derive for the multivariate Gaussian Mixture Model in this video. Hi and welcome to this new video. The agenda is that we will first recap on the derivations of the EM algorithm. Then we will look again at the joint distribution of the multivariate Gaussian Mixture Model. Then we will start with the E step and then continuing with the M step for all the 3 different parameters with detailed explanations. And in the end, we make a summary and some computational considerations when you want to implement this. So let's start with a recap of the EM algorithm. We derived the EM algorithm in order to perform a maximum likelihood estimate under latent data. That is because these cluster assignments are latent, so we don't know which clusters the point belong to. I mean, in 2 dimensions you could maybe guess it visually, but think of higher dimensions where it's almost impossible to visualize your dataset. So in order to circumvent our latent data, we have some sort of an iterative approach consisting of first an E step, which is calculating something that we called a responsibility, and we denote this as rho with lower index D and I. So it is some sort of the probability of the ith data point belonging to the div class. And we calculate this by evaluating the posterior on the latent variable set. So set given and then our observed variable, which is x. And here, in contrast to the univariate case, we have a multivariate, so a vector x, and assign this to the ith point. And then the crucial step here is that we perform the E step with an old guess of the parameters. And this theta vector is the collection of all the parameters that are involved in our Gaussian Mixture Model. If we then have the responsibility, we can perform the M step, which is the maximization step. And here we assign the new parameters to the arc maximum over all thetas, subject to some constraints we will consider later, over the following argument of the summation from I0 to n-1, so overall samples, times the summation from D0 to capital D-1 over all clusters of rho D upper index I times the logarithm of the joint distribution evaluated at these points. So we plug in the div class and the ith observation, and here we let the theta parameter vary, so this is where our theta comes in so that we can perform the maximization. With this back in our mind, let us also recall the joint distribution of the Gaussian Mixture Model. So the joint of the Gaussian Mixture Model. And as said, the Gaussian Mixture Model consists of a latent part and an observable part. The latent part is the set, which we call the cluster assignment, and the observable part is going to be the points in the high dimensional space. I call them X. And the cluster assignment affects the point I think that makes sense, because if we assign a point to the lower cluster, it is more likely to be in this region than in this region. Then our model has some parameters. For the set, we enter a probability or a class probability. For the x, we need some mu vector and a covariance matrix. And I use the index d here in order to denote that we need all of this capital D times, because we have D clusters. And then the fact that we are also provided with not only one point, but n data point can also be reflected in this graphical model by adding the index I here and then drawing a plate around these two nodes and indicate that we have this n times. And thus in every mixture model, the latent variable will be distributed according to a categorical given this pi vector here, and the x, so the values that we observe, will be distributed according to a multivariate normal over x, and is given by the mu set and the sigma set. So as said, if we have a different cluster, we also use a different normal distribution. Then let's also indicate that these are parameters to our model, and then we can use the directed graphical model to express the joint distribution by factorizing it. So we have the distribution over p and x, so over both, and this is essentially given as p of z times p of x given set, and then we can plug in what we have. So here we have the categorical over z given the pi vector, and then here we have a normal distribution over x given that we have mu set and sigma set, so the set mu vector and the set covariance matrix. And then we can plug in the definition of the two. For the categorical, we get the product over all the clusters that we have, and then we index the pi vector at the dev position and we raise it to the indicator function that set equals d, and this essentially will just return the set entry of the pi vector for a given value of z. And then we multiply it with the multivariate normal distribution, which will be 1 over the square root of 2 pi raised to the k, and k is the dimensionality of our problem. In the introductory example, we had a two-dimensional problem, and then we multiply it with the determinant of the covariance matrix, and here we need the set covariance matrix. Then we have an exponential term of -1/2, and then we have x minus mu set, so the set mu vector in brackets transpose, times the set covariance matrix inverse times x minus mu set, and then close and close again. And this is our full joint distribution for the Gaussian mixture model. And if we then also would want to account for this plate here with the n samples, we just apply an IID assumption and take the product over all i's. And with this some sort of as a refresh, we can then start with first looking at the E step. And the E step was calculating the responsibilities, so the row, lower index D, upper index I, and for this we have to query the posterior. We only have the joint, so let's try to express the posterior. And if we use Bayes' rule, then we can express the posterior, so P of z given vector x is P of x given z times P of z divided by P of x. And as usual, we have the marginal in the denominator. However, we can also just look at the numerator and make this some sort of proportional and calculate an unnormalized responsibility and then normalize it in the end. So we say this is proportional, and then we ignore the denominator of P of x given z times P of z. Well, and what we have here is nothing else than the joint distribution, because this is essentially the factorization that we also have due to the directed graphical model. So this is a P of z and vector x. Then let's denote that the responsibilities we're going to calculate are unnormalized. So we have unnormalized responsibilities, and I will indicate them with an tilde on top. So we have again row, lower index D, upper index I, tilde for unnormalized, and we calculate them by then plugging in the joint distribution. So we say that P of Z is D and X is the Xi of observation. And then important, we use old parameters for this. So we can evaluate this. And essentially what we have to do is then we plug this in here. And if we were to do this, then the first component here as set will just reduce to the def entry of the pi vector. So this is because you can also think of it this being a different indexing, let's say from C0 to D-1. So we have pi index D, and then we raise it to when D equals C, basically when we are in this def cluster, and then we only have the one entry left. So basically what we get is pi lower index D, the def entry of the pi vector, and then the rest of this expression will be mostly the same except for changing a set for a D. So we multiply this with 1 over 2 pi raised to the k times the determinant of the def covariance matrix times the exponential of -1/2 of the xi sample minus the mu def mu vector, and then transpose the def covariance matrix inverse, and then the xi of observation again minus mu d closing brackets, and then closing brackets again for the exponential. But of course we're not interested in the unnormalized responsibilities, but the responsibilities. And for this we can just normalize over the clusters so that we then get normalized responsibilities, and they are defined as rho d upper index I, so without the tilde again. And here we just take the unnormalized ones and we divide them by the summation over the clusters. So we'll just use a different index here and say this. And you can also think of it as the following. So if you were to save the responsibilities in a matrix, so if you say that rho is represented as a matrix, and then this matrix might be of the format that we have the number of samples in the rows and the number of clusters in the columns, then we would basically do a row normalization. So with this, we ensure that each row sums up to 1. And this should be reasonable because the responsibilities are some sort of the probability that a given sample point belongs to one of the clusters, and it has to belong to any of the clusters. So this has to sum up to 1. So this is some sort of a row normalization. And with this, we are already done with the expectation step. And this one is actually quite similar to the univariate case, but now in the M step, we will see some differences. So next up is gonna be the M step. And for this, let us set up the target function, which was this one here. So the expression with the double summation. And I will call this Q, and this Q depends on the theta vector that we can vary in order to maximize it. And that is based on the data set. And the data set was our n observations with k dimensions each, and also the old parameter set k that we used in order to create the responsibilities. And it was defined as the double summation and the summation over the clusters. And here let me switch to the index C. So it's going from C0 to D-1. So we have to also index the responsibilities with C and with I here. And then we have the log joint, Z being D and X being the observation, but here under our varied parameters. So then let's plug it in. We get the double summation I0 to n-1, then C0 to capital D-1, rho C I, and then let's do the logarithm of our joint. So the joint was this expression here, and if we perform the logarithm, then the logarithm turns products into sums. So here is some sort of like a multiplication. So we can take the logarithm of this plus the logarithm of this plus the logarithm of this one. So if we perform the logarithm on the product, then this turns into a sum and the logarithm propagates, and then the logarithm of this term here brings down the exponent in front of the logarithm and applies the logarithm to pi d. So we have then here an opening bracket, and we get the summation from d0 to capital D minus 1 of the indicator that d equals c times the logarithm of pi d. And here you see also the reason why I used a different index here, because otherwise we would have d twice. Then let's go back up and look at the expression that we have here. So if we were to apply the logarithm to this, we would get minus 1/2 of the logarithm of whatever is under the root here. And then we see we have another product here, so we can also just take the sum of it, and then the k goes up front again, and then we have, the logarithm 2 pi and the logarithm of the determinant. So we will get minus k over 2 times the logarithm of 2 pi, then minus 1/2 times the logarithm of the determinant of sigma d, and then the last term here is the exponent, and the exponential cancels with the logarithm, so we are just left with whatever was inside of this bracket here. So we get a minus 1/2 and then the ith observation minus mu d transpose, then sigma d inverse, and then the xith observation minus mu d, and then close it down, and then the closing bracket for this one here. And with this target function down, let us now denote our optimization problem. So here we just wrote it down in an abstract fashion, so that we want to say that the parameters at the next step are given as the arc maximum here. But now we want to make this more explicit and say that the pi vector at the next step, as well as the mu vector of the 0th cluster at the next step, all the way to the mu vector of the last cluster, so the d minus 1th cluster at the next iteration, and all the covariance matrices, so the 0th covariance matrices all the way to the d minus 1 covariance matrix at the next iteration, all of them, and this is already occupying the entire line, so we'll continue down here, is given as the arc maximum over, well, we have to vary pi from the RD, so pi is a d-dimensional vector, d is the number of classes, because for each of the class we have class probability. Then we have a mu d, which is chosen from the RK, and k is the number of dimensions, so this is for all d. And then we have the d covariance matrix, which is chosen from k by k for all these. And then we maximize our target function, so we take the arc maximum over the q function over the theta, and I will ignore the other arguments in order to make this a little more simple. It's already quite bloated, so this will be just q of the parameter vector theta. And we have some constraints, so we have subject 2, and the constraints are that our pi vector has to add up to 1, so the summation from c0 to capital D minus 1 over pi c has to be 1. And that is of course because we have some sort of like a probability mass that we have to distribute between the clusters. And we also have to ensure that the covariance matrices are symmetric positive definite. You could also say semi-positive definite, but here we will restrict ourselves to positive definite, and we need to ensure this for every d. So in essence, what we have is a constraint optimization problem. So we have a constraint optimization. So we can't just take the derivative and set it to 0. However, we can simplify it. And the first one that we're going to do is some sort of a relaxation, so that we will ignore this particular constraint. So we will ignore this So we will not account for the constraint that the covariance matrix has to be symmetric, positive, definite. So let me also note this down. This is an SPD constraint. So symmetric, positive, definite. And we ignore this because if we then later on implement this, we will just add some negligible amount to the main diagonal of the covariance matrix in order to ensure the symmetric positive definiteness. So I will say we ensure this, and I will put this in quotation marks, pragmatically. But then we still have one constraint left, and we have to account for this. Since this is just like a simple equality constraint, we can build a Lagrangian and then take the derivative of the Lagrangian with respect to each of the parameters and with respect to the multiplier and set it to 0, and then the constraint is accounted for. So the solution is here to build the Lagrangian, and the Lagrangian is given as Q. Also, I will use the same letter. I will just put a hat here in order to note that it's the Lagrangian. And this one is on the parameter vector and on a Lagrange multiplier, a scalar Lagrange multiplier. And it is defined as Q of lambda, so our original target function, plus lambda times 1 minus the constraint basically, or the constraint rearranged for 0. And here we have the summation from C0 to capital D minus 1 over the pi C. And with this, we have an augmented Lagrangian, and this allows us to get an unconstrained optimization problem. So we do this to get an unconstrained optimization problem. And with this, we can follow the strategy that I said before, take the derivatives and set to 0. So this is what we will be doing. Take derivatives and set to 0. And for this, let us take another sharp look at our Q function and see what kind of derivatives we are going to take. So we will take a derivative with respect to pi, because this is one parameter. We will take a derivative with respect to mu, which is another parameter. We will take a derivative with respect to sigma, which is another parameter, and with respect to lambda, which is the multiplier. But we won't take any derivative with respect to k, with respect to the dimensionality, and also not with respect to pi. So every time we will take derivatives, this will turn out to be 0, so we can just ignore it in the first place and say that our target function is given as this here up to an additive constant. Then let's start by maximizing our Lagrangian, and we will do this step by step. In the first step, we will maximize with respect to the pi vector, so point A, maximize with respect to the pi vector, which was our class probabilities. And recall, the pi vector is a d-dimensional vector, and here we will maximize with respect to one element of it, and I will call this one element pi e, so this is one element of the pi vector. And with this formula, you can then calculate all of the elements in the pi vector or calculate the update of it. So think of it as an arbitrary one, but it is fixed for this derivation here. And here we have to take the derivative of the q hat with respect to pi e. So let's look at what the derivative will be. For this, we have our Lagrangian, and we see that pi appears here in the multiplier term. Let's care about this in a second, but first look at the original target function. And then we can go up here and see if we apply the derivative, then it will propagate over the two summations. Then it will hit the responsibilities, but in this case, they are just considered as a multiplier. And then it is applied to the sum of the terms here, and pi appears only in the very first term, so all of these other terms are constants with respect to deriving it with respect to pi e. So we just have to consider the derivative with respect to this term. So let us note this down, that we have basically the summation from I0 to capital N minus 1, and then the summation from C0 to capital D minus 1. And then we have our responsibilities, and then we have an opening bracket, and then here we have our derivative that propagated all the way to here, and then we have the other summation from D0 to capital D minus 1 over the indicator that D is C times the logarithm of pi d. Then let's close this down and also put some brackets here because we now have to consider the derivative of this multiplier term here. And the derivative propagates over the lambda, of course, because it's just a multiplier. And then if we derive 1 with respect to pi e, this will be 0 because 1 is just a constant. So let's propagate this further and say that we have minus lambda times the derivative with respect to pi e. And then here we have the summation term over all the components here. And a really important remark, again, we take the derivative with respect to one element of pi, so the pi e, and here we also have pi index, so essentially this is also one element of the pi vector, but these are different indices. And we also see this if we perform this derivation outside of the big expression here, so to have it less cluttered. So essentially what we will be doing is taking the derivative with respect to pi e of the summation from d0 to capital D minus 1 over the indicator that d is c times the logarithm of pi index d. And we see that this derivative will also propagate over the sum. So essentially we have to take the derivative of this one here. So let me also extract this further. So the derivative with respect to pi e of the indicator that d is c times the logarithm of pi d. Well, we see the indicator, there is no pi in it, so it's also just acting as a multiplier. So essentially we have to take the derivative of the logarithm of pi d with respect to pi e. So extracted even further, we get the derivative with respect to pi e of the logarithm of pi d. And now it is crucial to remind yourself that these indices are different. And you can also think of it as some sort of like a chained relation. We take the derivative with respect to pi e, and we actually have a pi d. So we have to apply the chain rule. And the chain rule holds as following, that we first take the derivative of the logarithm of pi d with respect to pi d, and then we derive pi d with respect to pi e. And these are derivations that we can easily perform. So in this case, the derivative of a logarithm with respect to its argument is 1 over its argument, so 1 over pi d. And here we are getting the Kronecker delta, which is the Kronecker delta index dE. And this works as following. The Kronecker delta is 1 if these two indices are identical, and it is 0 if they are different. And that makes sense, because we derive with respect to one entry, but this one entry is fixed. And this derivation will only be non-zero if the upper argument is actually the same as we want to derive with respect to, because otherwise it would just be a constant. And then we can, recursively plug this back in. We will do this in a second, but before, let us also consider this one here. And based on the knowledge we just derived here, we can just, apply it here. So essentially what we will be getting is that the derivative propagates over the summation. So we have the derivative with respect to pi e of pi c, and we see that's already what we did here. We get a Kronecker delta, and this time with the indices c and e. Okay, let us plug this into the derivative that we had to do. So this will be equal to, first we have the summation from I0 to capital N minus 1, then the summation from C0 to capital D minus 1, and then we have our responsibilities, and then we have the summation from D0 to capital D minus 1, and then we keep the indicator that D is C, and then we had this expression 1 over pi d times the Kronecker delta dE, and that is quite a long one. And then here we get minus, well, this will be the summation over the Kronecker delta, so minus lambda times the summation from C0 to capital D minus 1 over the Kronecker delta CE. Okay, now we have the Kronecker delta in here, and by the definition of the Kronecker delta, it inhibits a really interesting property that if it appears in the summation over D, for instance, and we have the Kronecker delta with another index, which is actually one element, which we would be summing over, this essentially breaks down the summation into only the one contributing term. And it makes sense because we do the summation of all the d's. So d is 0, d is 1, d is 2, d is 3, all the way to capital D minus 1. And every time the Kronecker delta is 0. So we just add up 0, 0, 0. Only in one particular summand, we're getting a non-zero contribution. So we can also just get rid of the sum, right? So because this is only one term that will be relevant. And you can also think of it as somehow killing the summation. So we trade the Kronecker delta with the summation. And whenever an index d appears, we change it to e, or to the other one that is in the Kronecker delta. So we have an e here, and then here we get the same idea, just with the fact that we have a contribution of 0 plus 0 plus 0, and only one times it will be 1. So this entire term will turn out to be 1. Okay, noting this down, we keep the double summation that we had before, and we essentially got rid of one summation. That's great, because we had so many in the first place. So we have the responsibilities and then the indicator that E is equal to C, and then times 1 over pi E, and then still keeping this brackets, and we have a minus y. So here we have another component which actually acts like a Kronecker delta. So it's the indicator function. And recall, the indicator function is 1 if the statement is true, and is 0 if not. So we can also think of it as some sort of Kronecker delta, at least in this discrete sense. So here this is equal to the Kronecker delta EC. And by just doing what we did before, we can kill the summation over C, right? Because it acts like the Kronecker delta. So we kill the summation over C, we kill the Kronecker delta, so we kill the indicator function, and change all indices that have been C before to E. So we have an E here. And that allows us to have one sum left. That's amazing, right? So we have the summation from I0 to capital N minus 1, so over all our samples, over rho EI times 1 over pi E, and then minus lambda. And just another remark, changing the indices, of course, doesn't change the responsibilities. So these are still like the matrix structured objects, because it has like two indices. If you think of it like visually, it's still the same matrix. You just use a different index in order to address the element inside of the matrix. Then the point that we actually haven't looked at yet is the fact that we have to maximize. So we have to set the derivative to 0. So that's what we will be doing here. This has to be equal to 0, because that's how we're getting a maximum. And then we can rearrange a bit. First, I will bring the lambda on the other side of the equation, so I just plus lambda. And the observation that pi e does not depend on I, so there is no index I in it, we can just move it in front of the summation. So we can move it here. And by these rearrangements, we arrive at the point that we have 1 over pi e times the summation from I0 to capital N minus 1 over the responsibilities has to be equal to lambda. And this quantity here, the summation over the samples for a certain class of the responsibilities, appears quite often in the following derivations. So I will just give it like a shorthand notation and call this gamma e, which is the class responsibility. And this name is hopefully somehow meaningful, because it's all the responsibilities from all the samples added up. So in other words, how much do all samples contribute responsibility mass towards the Eve class? Well, with this down, the equation is quite simple. So we have a gamma e over pi e is lambda. Yeah, then rearranging, we get that the pi e is gamma e divided by lambda. But what is this? What is the lambda? We know that the Lagrangian multiplier is used to ensure the property that our pi vector has to add up to 1. So in order to account for it in our constraint optimization by the help of the Lagrangian, we also have to take the derivative of the Lagrangian with respect to the multiplier. So let's do this. I will take the derivative of q hat with respect to lambda. Then that's going up. We see we have a lambda here, so this will yield this expression. And in the original target, of course, there is no lambda appearing because we added it in the Lagrangian in order to account for the equality constraint. So what we're getting basically is 1 minus the summation from c is 0 to capital D minus 1 over pi c, and this has to be equal to 0. Well, if we rearrange this, then we essentially get our equality constraint. That's always with the Lagrangian in equality constraint optimization. So we have the summation from c is 0 to capital D minus 1 over pi c equals to 1. But the question is now, how can we use this constraint in order to solve for lambda? And the idea is that here we found a solution for pi e, so we can just plug in the solution here. So the summation is basically over all the components of pi, whereas here we found the solution for one of the components, so it also holds for other components, not just for the Eve component. Let's say, for instance, E is 3, but this also holds for E is 4 and E is 5. That is because we fixed the component we're taking the derivative with respect to, but it can be arbitrary. So let's plug this one back into the summation. And if we do this, then we get the summation from c is 0 to capital D minus 1. And now we have to take care the index change, because here we have a pi c and there is a pi e. So we have an gamma c over lambda is equal to 1. Well, lambda does not depend on the index c. So in essence, this is identical to saying lambda is the summation from c0 to capital D minus 1 over gamma c. And now what will this be? So if we go back to the point where we said that the responsibilities can be viewed of as a matrix, for which we ensured that the rows add up to 1. So each of the row is 1. And what we now did is calculating the class responsibilities. So we summed up all the samples. So basically get this row vector here, which has the number of classes or clusters, but has only one dimension in the sample space, basically. And if we now want to take the sum over this, what will come out? So we know that each of the rows will be 1. So this is 1, this is 1, and so on and so forth. And if we sum up n rows that are 1, or the total sum of all the entries, we are getting n. Because the total responsibilities of all the samples can be n at maximum. So in essence, what this will be is n. And then we figured out that the Lagrange multiplier is n. We reached the final solution for the update equation for the class probability, which is that pi e is gamma e divided by n. And that's also a reasonable result, so it'd be good that the class probability of the Eve class is the class responsibility in ratio to the total responsibility that's distributed, or in other words, the total samples that we have. Next up, stage B, we will maximize with respect to the mean vectors. So we maximize with respect to, and then we have a bunch of mean vectors. So the 0th mean vector and all the way to the D minus 1th mean vector. And recall all the mean vectors. So I just use the lower index D here for any of this D mean vectors is a k-dimensional vector, so because we are in a k-dimensional space. And for this, let's use a similar strategy to before. We don't maximize with respect to all of the mean vectors at the same time, but let's take one. So we have the mu e, which will be one mean vector out of the collection that we have here. And we see that if we then have an update equation for mu e, we can just like vary mu e and take any of the mu e's we want. So basically what we have to do is we have to take the derivative of our Lagrangian with respect to mu e. And note, now we're taking the derivative with respect to a vector. So in the end, this will be equal to a 0 vector because it's like a vector valued equation then. So let's go up and we see that in our Lagrangian, the multiply term does not contain the mu. So we can just focus on the original target. And in the original target, well, the derivative propagates over the two sums again. And then let's consider this entry here, or like these entries. And this one is only pi, so there's no mu. This was the constant in the first place. There's only sigma here, but bingo, there's mu. So let's just write this down abstractly. So we have the double summation again, I0 to n minus 1, and then C0 to capital D minus 1, and then rho Ci. And then we have the opening bracket, and here we have the derivative with respect to mu e that propagated all the way to here. And then we apply this to minus 1/2, and then here we have the expression of xi minus mu d in brackets transpose, and then we have sigma d inverse, and we have xi minus mu d. Then let's close this down, another closing bracket and another closing brackets. Then we can apply the derivative, and here we see that we have a quadratic form in multivariate fashion. So we have to apply the product rule. But we also see that if we take the derivative of this expression, then we have different entries. So here we have an arbitrary d again, so which is one of the collection here. And we take it with respect to one fixed. So we again get our Kronecker delta in the end. So we just do the chain rule trick. So we say that the derivative, and I will just use this here of, in brackets, whatever it is, with respect to mu e is the derivative of whatever we had here with respect to mu d, and then the derivative of mu d with respect to mu e, and we can already evaluate this one. So if we derive this vector with this vector, this will give us the identity matrix times the Kronecker delta dE. And since we will obviously get a vector here and then multiply it with the identity matrix, we can ignore the matrix and just look at the Kronecker delta. But then we also have to take the outer derivative. And for the outer derivative, well, let's look at the format that we have here. So we would first fix the second term where the mu involves and take the derivative of the first. Then we would get a minus sigma d inverse and then this term. And if we then fix the first one and derive with respect to the second, we get this term transpose sigma d inverse and then a minus from here. And since we know that sigma d is symmetric positive definite, which was one of the constraints, the inverse is also symmetric, so that we can just swap the orders of multiplication with a vector, whether it's like multiplied as a row vector from the left or a column vector from the right. So in essence, this would yield that we have 2 times sigma d, or minus 2 times more precisely, sigma d inverse and then this term. So long story short, what is it that we are getting? So we have the summation from I0 to capital N minus 1, and then the summation from C0 to capital D minus 1 rho Ci. And then we get, well, we have the minus 1/2 that we had before, and then we get our minus 2 sigma d inverse times xi minus mu d. And I just see that I kind of confused myself with the indices. Of course, we don't have another index d here, so this should be index c for all of the cluster components. And then I should also probably adapt the one that we have here. So this is mu c, and here we have the mu c, and this will then also yield a delta ce. And then adapting the result we have here would yield where we should be, right? Okay. And then, of course, don't forget the Kronecker delta CE. And then this all still has to be equal to the 0 vector. Okay, then let's try to simplify. We see that the minus 1/2 cancels with the minus 2. And then we apply the force of the Kronecker delta again. So we kill the Kronecker delta, and then we are allowed to kill the sum, but we have to change the indices. And with this down, we are only left with one summation. Yay, that is nice. So we have the summation from I0 to capital N-1 over rho lower index E upper index I, and then multiplied with sigma then lower index E, so the E sigma inverse times the xi of observation minus the mu E, and this has to be equal to the zero vector. And what we see here is that we have a summation over I, but our sigma matrix does not depend on I, so we can move it in front of the summation. And now this might get a little bit confusing because we have the same symbol for summation and covariance matrix, but I hope that we use some sort of like the indexing for the summation and the double underscore for the sigma, and with this it should be able to identify the two or distinguish between the two. So doing this will give us an sigma E inverse times the summation from I0 to N-1, then we have the rho EI times the xi minus mu E is equal to the zero vector, or has to be equal to the zero vector. And then we see we can get rid of the sigma E inverse here by left multiplying with sigma E. So we take a left multiplication on both sides of the equation with sigma E, and then this cancels, this becomes the identity matrix, and the identity matrix multiplied by a vector is just the vector itself. And on the right hand side of the equation, multiplying sigma E with the zero vector, which is, will just give us the zero vector once again. So with this simplification, we then arrive at the summation from I0 to N-1 over rho EI times the xi minus the mu E is equal to the zero vector, or has to be equal to the zero vector. And then let's split up the subtraction here into two separate summations. So we get that we have a summation from I0 to capital N-1 over rho EI times xi, and then minus a summation from I0 to capital N-1 over rho EI times mu E, which has to be equal to 0. And then we see mu E does not depend on I, so we can move it in front of the summation, and then the summation over the responsibilities with respect to the samples is just giving us the class responsibilities gamma E that we defined earlier. So in terms of this, and then maybe also putting it on the other side of the equation, we are getting that the summation from I0 to N-1 over rho EI xi is equal to gamma E mu E, and then there is only one step left to get the mu E, which will be saying that mu E is 1 over gamma E times the summation from I0 to N-1, and then the responsibilities with the respective observations. And with this, we have our second update equation for the EM algorithm. Last up, we have the maximization with respect to our covariance matrix. So I will call this stage C, where we maximize with respect to, and then we not only have one covariance matrix, but we also have a bunch of them. So the 0 all the way to the d-1. And recall, the covariance matrix is a matrix from the space of k by k dimensional matrices, and it additionally has to be symmetric, positive, definite, but we will ensure this pragmatically, so we just take it as an arbitrary k by k dimensional matrix. Okay, similar strategy to before. We take one particular covariance matrix, let's call this sigma E, which will be one of the covariance matrices that we consider here, and then we can just use this result to derive it for any other of the covariance matrices. And what we have to do for this, we have to take the derivative of our Lagrangian with respect to sigma E, and this will yield something, and in the end, since this is a derivative of a scalar with respect to a matrix, this is a matrix valued equation, so it has to be equal to the zero matrix in order to be a maximum. So let's go up to our Lagrangian, and we see that the sigma does not appear in the multiplier term. It only appears in the target function. So let's go here. And then we see, well, the derivative again propagates over the first two sums over the responsibilities. And then what kind of terms involve the sigma? We don't have any contribution from the first term. There's just a pi vector in it. Then we have the overall constant. But then we have two terms where it appears in, and this is the log determinant, and then here this quadratic construct. So let us again write down in an abstract fashion how the derivative looks like. So let's see. Okay, we get the derivative and then we keep our double summation. Again, take care, there's a similar symbol for summation and the covariance matrix. So here the sum from C0 to capital D minus 1. And then we have our row Ci, and then the first derivative with respect to sigma e of minus 1/2 of the log determinant of sigma e. And then we have the other term, and then plus, I will go into the next line, but this still has to hold equal to the zero matrix. And here we have the derivative with respect to sigma e of minus 1/2, and then the quadratic construct, so an xi minus a mu c in brackets transpose times sigma c inverse, and then we have the xi minus the mu c, and with this we can close again and another close, and this has to be equal to the zero matrix. This derivative here propagates over the minus 1/2 in both of the cases, but then it requires some more advanced matrix calculus in order to take the derivatives. However, this is quite close to what we did in the maximum likelihood estimate for the multivariate normal, so please check out this video if the derivatives I will bring up now somehow sound strange to you. But one important addition to what we did in the maximum likelihood estimate is that we now have to consider taking the derivative of the sieve covariance matrix with respect to the Eve covariance matrix. So we have the same idea as before. We do an outer and an inner derivative, yielding the Kronecker delta in the end. So I will just perform or copy these derivatives from the video on the maximum likelihood estimate. So in essence, we keep our summations I0 to n minus 1, and then C0 to capital D minus 1. And then we have the row Ci, and then we have the minus 1/2. And this derivative will be sigma C inverse times the Kronecker delta CE. And I will just use an opening bracket here. And then we have plus minus 1/2. And this derivative will be a sigma C inverse and then an xi minus mu c times an xi minus mu c in brackets transpose. And also take care, now we have the transpose on the second vector, so this is in essence an outer product yielding some sort of a matrix here. And then we multiply with sigma c inverse again, so this is basically the outer derivative. And then for the inner derivative, we also get the Kronecker delta on the indices C and E. And then let's close this down and remind ourselves that this has to be equal to the zero matrix. And if we multiply with minus 2 on both sides of the equation, we can then basically ignore this prefactor. So this simplifies it a bit further. And then we can apply our Kronecker delta again, because we have it in both of the summands. So kill the Kronecker delta, change the indices to E, all the way to E, yes, and also here, and then kill the summation. And this greatly simplifies the equation further. So we then have left the summation from I0 to capital N minus 1. And we have a row EI multiplied with opening brackets of a sigma E inverse plus a sigma E inverse and this outer product construction. So xi minus mu e, and then we have the xi minus mu e in brackets transpose times sigma E inverse, and then let's close it, and this has to be equal to the zero matrix. And I see there is a small mistake here. Actually, the second derivative, or the derivative of the second term here, should yield a minus. So we have a minus here and then also minus here. Okay, then we can split out the summation here into two terms. So once in this term here, and then also with this term using the responsibilities once again. So then we get the summation from I0 to capital N minus 1 over rho EI times the sigma matrix E inverse and then minus summation from I0 to capital N minus 1 over sigma E inverse and then the outer product construction that I will just copy again. And then we have another sigma E inverse, and this has to hold equal to the zero matrix. And then we observe that the sigma E inverse is basically independent of the summation of I. So we can just make some clever bracketing, and in this particular case, we can just bracket it like this. But here we have to move the sigma E inverse in front of the summation and then use a clever bracketing. And of course, we should be having the responsibilities here, and then we're good to go. Now let's apply the clever bracketing here. So we have first the summation from I0 to capital N minus 1 over rho EI. Then we set the bracket and have our sigma E inverse and then minus, and then let's move this in front of the summation. So we have a sigma E inverse and then an opening bracket with our summation from I0 to capital N minus 1. Here we have our rho EI, and then we get the outer product construction once again. So like this, and then the bracket closes and sigma E inverse is outside of the summation. And the reason we did this is that we actually want to find an expression for the Eve covariance matrix. However, here we have the inverse of it. So we somehow have to get rid of the inverse and convert this into the non-inverse sense. And we can do this in terms of multiplying with the sigma E matrix, both from the left side and from the right side. So we make a left multiplication with sigma E and a right multiplication with sigma E. And then, considering just the second term here, we see that if we multiply a matrix with its inverse, this will just give the identity matrix. So we get the identity matrix here, we get the identity matrix here, we get, due to the right multiplication, the identity matrix here, and then, that's the important point, here we are getting the Eve covariance matrix, but without the inverse. And that's great, because then we can rearrange for it. Additionally, we can also see that this hello is our class probabilities once again. So let me note this down in the format we have right now. So we have that sigma E times gamma E minus the summation from I0 to capital N minus 1 over rho EI times and then xi minus mu E times xi minus mu E in brackets transpose has to be equal to the zero matrix. Well, and the last step is quite simple. We put this on the right-hand side of the equation, divide by the class probabilities, and voila, we have our last update equation, which is for the sigma E, and it's 1 over gamma E times the summation from I0 to N minus 1 over rho EI, and then the outer product construction, and my angular brackets are getting quite ugly now. Excuse this. Hope you can still understand the semantics here. And then let's finish it off. And with this, we have found the last update equation. And this update equation is a valid way to compute the new versions of our covariance matrix, but it has the disadvantage that it will not run fast if you implement this in the programming language of your choice. That is because, think of the following point, you have to do the updates for all of the clusters. So you probably have some sort of like a looping over the clusters. Then you have your summation, so you have your looping over the samples. And if you have a lot of samples, let's say 10,000 or so, this is quite a long loop. And then within each of the loop, or within each element of the double for loop to be more precisely, you perform this outer product construction. And that can be quite costly. especially if you implement this in languages like Python, which have a lot of loop overhead. And what we are doing now is to improve the computational performance by making an equivalent statement for this in terms of some clever linear algebra manipulation. And the reason why the version we will come up is faster is because it will be using really highly efficient numerical kernels that can take advantage of modern CPU architectures. So you will see runtimes that are fractions of what you would do if you would implement this naively, like the one that you have right here. And the idea is quite similar to what we also did in the maximum likelihood estimate for the multivariate normal distribution, where we, instead of considering single data vectors, we considered one big data matrix. And we called this data matrix capital X double underscore because it's a matrix. And that is the data matrix, sometimes also called the feature matrix. And we will give it the following layout. So in our case, it has the number of samples in the rows and has the number of dimensions in the columns. Sometimes people use the transpose of it, then you have to adapt the findings that we do. But in essence, it's just a collection of all the samples that we have in a data matrix. And view it as following, so that you have the 0th data point in the first row, then you have the first data point in the second row, etc. pp. And then all the way to the end, you have the n-1 point that you use here. Of course, these are vectors that we have here. And then basically what we are doing in our outer product construction is to subtract the mean from all the samples. So we are basically centering the data points or the feature vectors that we have. And for this, we have to subtract the mean vector. And recall the mean vector, or more precisely, the mean vector of the Eve class, is given in our case as a column vector, and it has in the rows the number of dimensions, which matches with the number of columns that we have here. And then, of course, it only has 1 here, because like, what is the other dimension? It's just a vector. And basically what we have to do is we have to create a centered data matrix. And this centered data matrix, I will just give it the tilde here in order to know that it's centered. It has the index E because it's for the Eve class, because this of course differs between the different classes because they have different means. And this one will be basically in each of the rows that we have here the 0th data vector minus the Eve mean vector and so on and so forth. But how can we achieve this? And for this we will use some linear algebra magic in order to blow up this matrix, because if we have another matrix which is of the same shape as the data matrix but has the mean vector in each of the rows, then we can just component-wise subtract it. So what we will be doing, I will call this a blow up, so that we can create a matrix which has the Eve mean vector in all of the rows. So we just copy it n times basically to mimic the shape of our data matrix. And we can get this shape by multiplying a vector that contains only ones and is of size n, which is the number of samples here. And we multiply this with mu e transpose, and by this outer product construction, we can then blow up this given matrix here. And then we can get our centered data matrix by just subtracting these two, saying x minus 1n mu e transpose. Of course, this is not how you would implement it in Python or Julia, because this idea of multiplying with a vector of dimension n with only 1 entries can be represented by efficient broadcasting. And we will see this in the next video when we implement this in TensorFlow. And then a quick recap from the maximum likelihood estimate video. So in the MLE video, we said that the covariance matrix is then found by taking the centered data matrix transpose times the centered data matrix, because then essentially we are getting the multiplications that also appear here. And remind yourself, here we had an outer product, so we had vector times vector transpose. And here we are doing a matrix multiplication, which has the transpose on the very first matrix. And of course, this differs if you use a different layout for the data matrix. And the reason this works, or the reason this is equivalent to the term where we would had the summation, is that whenever we do matrix multiplication, there is a contraction over a dimension. So in this contraction, we have a summation, and then we kind of move the explicit looping that we would do in Python into the low-level numerical kernel that is highly efficient, or probably more efficient than we would ever want to write a matrix multiplication. But now, this is not what we are doing here, so this is not here, because remind yourself that it is not just the sum over the outer product construction. We also have to multiply it with the responsibility here. And we can also efficiently represent this by introducing a responsibility weighted centered data matrix. So that's a mouthful. Let's call this the responsibility weighted centered data matrix. And for this, let me use the name x hat. And I will define x hat as, and for this we now have to remind ourselves that when the ith sample is subtracted from the mean, we multiply it with the ith responsibility, and we also in the eth class here. So we basically have to element-wise multiply each of the entries in our centered data matrix with the corresponding responsibility. So we have a responsibility vector that I will call row E here, and this row E is just, well, it has all the entries here. So this is, let me put this explicitly, this is row E0, row E1, all the way to row En-1. And it has the number of samples here. And then, of course, 1 because it is a vector. And basically what we have to do is we have to multiply the first row with the first entry. And for this, we have to blow up this matrix to be of the same shape as the data matrix and also the centered data matrix. And we can do this as following by right multiplying it with the one vector again. And of course, in implementation, you would use some sort of broadcasting. In essence, this will be given by using the row E vector and then right multiplying it with a one vector, which has k entries, which is equal to the number of dimensions that we have. And this matrix, which is of n by k, we then have to element-wise multiply with our x tilde, our centered data matrix, and then we get this responsibility-weighted centered data matrix. And then we can finally replace this here, and I will just indicate this here real quick, that all this can be then represented as x tilde transpose x hat, or also x hat transpose x tilde, and then we just have to divide by the class responsibilities, and then we're good to go. And we have the optimized version given as the Eve covariance matrix is 1 over gamma E x tilde transpose times x hat. And I just see that we of course should use the indices E here too, and we need a transpose there, and then also correspondingly the indices E here. Let me double check, but I think this should be, yeah, it should be fine now. Now it should be correct. And with this optimized version, we can then come up with a summary of the EM algorithm for our multivariate Gaussian mixture model. It was a long journey, so it consists of first the E step, where we had in the first stage calculating the responsibilities or the unnormalized responsibilities. So we have the row lower index E, upper index I, tilde, and I will also stick to class index E here, because this is what we used in the maximization then. And this will be given as pi E, so it's using the old estimate of our parameters, multiplied with our multivariate normal, evaluated when x is the ith observation under the mu vector from the Eve class and the covariance matrix from the Eve class. And if we calculated this, we can then normalize them by saying the normalized version is the unnormalized version divided by And let me introduce a summation here. Just use an auxiliary index here from D0 to capital D minus 1 over rho di unnormalized. And remind yourself that this is the rho normalization. And then let us also calculate the auxiliary quantity, the class responsibility here, by just summing up over all the samples that we have in our responsibilities. And with this, we're good for the E step. And then let's just use the M step. And the M step consisted of 3 updates. First, for the pi vector, which is pi e, that is given as the class responsibilities divided by n, which is the total responsibility mass. Then for the second point, we had the update for the mu e, which was 1 over gamma e times the summation from I0 to capital N minus 1 over rho e I. And then we had our xi observation here. And then the last one, which took us quite some time, which I will also write down in the optimized version. And here we have that the update for the Eve covariance matrix is given as 1 over gamma e. And then we first have the center data matrix, which is x minus 1 times mu e transpose, and then closing, and then transpose. And then we have our responsibility weighted center data matrix. So again, the center data matrix. And then we Hadamard or element-wise multiply this with the rho e vector multiplied with 1k transpose, and then closing brackets and closing brackets. And that is it. These are the update equations that you have to use. And implementation-wise, you have to do some sort of an iteration. First E step, M step until convergence. So implementation would be that you start with guesses, and then E plus M until convergence. And if you watch the video on the sieving for the EM algorithm on the univariate Gaussian mixture model, you can, for instance, use the likelihood or the log likelihood as a measure of convergence, so that if this doesn't change anymore or only negligible amounts, then you can stop the algorithm. And also another remark, also in comment to the sieving video, that these guesses are crucial. And they are even more crucial than in the univariate case. So it is really important that you start with guesses that are kind of close to what you would expect the algorithm to find in the end. Because due to the fact that we have to ensure that our covariance matrix is symmetric, positive, definite, it can be hard to ensure this just pragmatically if the guesses are really off. And we will see this in the next video, all of it, when we implement the algorithm in TensorFlow, so stay tuned for that video. If this video contained any confusion or if you have questions, then please write a comment. I would be happy to help you. If you enjoyed it so far, then also consider liking and subscribing to the channel. That's a good chance for you to show me that you like these kind of videos. Here you can also select similar videos, and then I hope to see you next time.